so thank you for the introduction, Romain. If I can just say just a couple of words. I consider myself to be a principal systems engineer these days. I'm the director of Clarity SE, whose mission it is to train people in the Arcadia methodology using Capella. And on top of that, I'm a principal systems engineer working for KBR. So I have quite a busy schedule, but I enjoy it all because I get to talk about systems engineering a lot. So today what I wanted to present is how to use Capella in the context of a transport or infrastructure project. Because I think there are some specific, domain-specific things that we should and should not be doing when using Capella. And this is, I guess, a view that I have formed over the years, having worked on quite a number of transport and infrastructure projects now, about what I can see works well and what I can see perhaps might be best put to one side for the next project. So first what I wanted to do was start with an Arcadia overview. So just looking at some of the people on the list, I can certainly see that there are a lot of people that would already be familiar with Arcadia and at least have a base level understanding of Capella as well. So I'll move through these slides reasonably quickly. However, I do want to make sure that I don't leave anybody behind. So Arcadia, what does it mean? Well, what it stands for is Architecture and Design Integrated Approach. That's a bit of a mouthful, but Arcadia basically includes a number of elements of a systems engineering framework, a systems engineering methodology, and also a set of language formalisms. So when you stir it all together, you can't call it a framework, you can't call it a methodology or a language. So approach is what we call it. And the idea is it helps us do the architecture modeling as we work through the life cycle from requirements analysis all the way through to IVV and test. So Arcadia itself has been a lot of thought put into this particular approach. So there you can use certain parts or not use certain parts as we deem necessary. It's quite often presented as you've got to do all the things to work through the methodology, but that's really just so that you can see the full picture of what's available. So there are four main top-level perspectives. I tend to use the old language, layers, to Arcadia. The operational analysis, where we try to identify what it is that the users actually need without any concept of the technical solution. The system analysis, where we sort of draw a box around the scope of the project and work out what's in and out of scope. The logical architecture, which is best understood as a conceptual architecture. And the physical architecture, which is more or less how we're going to go about building the thing. So first question is, well, which layers to use? For which I have to give the most important answer any system engineer could ever give. All right, it depends. It depends on a lot. So what does it actually depend on? Okay, so we need to ask ourselves a few questions. We need to ask ourselves, how much will a particular layer or perspective add value? How well is the solution already understood? How will it help us through the life cycle? What's the nature of the system that we're actually trying to describe? Is it a single platform or is it a multi-site deployment? How well is the scope of each of the different teams? How well is that understood? And the most important question is to take a step back and ask ourselves, well, why is it that we need to use modeling to answer any of these questions in the first place? So some things to keep in mind. All right, so I'll try to flick through a couple of these slides reasonably quickly, What I'd like to do now is just talk a little bit about each of the layers and how I think they may or may not apply to transport, transport and infrastructure. So operational analysis. So I mentioned that it was it's what we use to define what it is that the end users need to achieve without any concept of the technical solution. So what that means is that it can be a useful layer if you need to define the ConOps, and it's therefore useful in getting a really clear grounding captured in your system model somewhere that you can trace to what those needs and what those processes are. So that's great. However, from a transport and infrastructure perspective, I think that's very, very conceptual. Many transport and infrastructure projects. I think we can't forget that we've been building trains for the last several hundred years, and we've been building buildings for the last several thousand years. We've got a pretty good idea of how to use them. So a full-blown operational analysis is probably not necessary. Right? If the way that an organization is going to work within the space is already reasonably well understood, you don't need to do a lot of work. There might be some key areas that you need to focus on, and maybe you can do a little bit, but you're going to burn a lot of hours trying to capture a complete greenfields ConOps if you're working on a brownfields project. So I would suggest be careful here, and really, if you're genuinely starting with a clean sheet, this layer will probably add some value. However, if you already have a well understood operating model, just consider focusing your efforts. Next, system analysis layer. So this is the black box analysis, where we draw that conceptual box around what's in scope and what's out of scope. We define and then we define the interfaces between the parts of technical solution that are in scope and the interfacing actors or somebody else's scope of work. So that's fantastic, and we can at this point also start to identify some very, very top level verification or indeed validation scenarios. From a transport perspective, I actually think this layer is very important, far more important than the operational analysis layer, and that's because drawing a nice, simple, clear box around what is in scope, what is out of scope, and what the interfaces are with other subsystems or organizations that are not within scope is incredibly important. And it is incredibly important because quite often transport and infrastructure projects are brownfields. So we need to be clear about what the precise scope is and what is definitely not in scope. Okay, so it doesn't provide a huge amount of clarity in terms of what the technical solution is or how we're going to deploy to multiple sites. But I think drawing that box and being able to say, this is in scope, this is out of scope, here are the interfaces, and therefore build up an initial set of contract level requirements, and you can start to then work on on initial cost estimates. I think that's very valuable. Logical architecture layer. I've done a whole nother presentation on specifically the logical architecture, and I could easily talk for an hour just about it. I'll try to be quick. The purpose of the logical architecture is to define conceptually how the system is going to work. What that means can be very, very different depending on your project to somebody else's project. So we're just trying to group the functionality of the system into sensibly organized sets of related functionality, and we do that on the basis of what the work package breakdown might look like, some assumptions about technical solutions, what technology is available, the deployment of the subsystem, and so on. And we can do this with a view to focusing on how the system is going to work, rather than how it's going to be built, perhaps for a product line. We might wish to generically define how a system works, rather than generically define it so that if you have differences between your products within your product line, you've got this generalized architecture. You could also use the generalized architecture to keep things resistant to technological change. And you can also potentially use it to help manage the breakdown of responsibility between individual design teams. Just a very quick view of what some of these conceptual logical architectures might look like. For a scope breakdown, you might have different work packages with borders drawn around the outside of the work packages, and work out what's in scope and what's out of scope, and what the interfaces are between those work packages. I've seen that done. That's quite useful. Solution class, where you're just trying to keep a generalized architecture, so you know how things fit together. Again, I don't think that one's overly useful for transport, because we kind of know how trains and buildings work. Detailed technology agnostic solution. I think this is one potential approach that I think would be useful in a transport context, because we can have a look at how we expect the technical solution to fit together, and whether or not we've accounted for all of the requirements that we have. Deployment agnostic. We start to sort of cross over a little bit here into the realms of something that the physical architecture can also be good at, but you might want to be a little bit more specific with your logical architecture and define precisely what the technical solution is, and then deal with the deployment in the physical architecture. That's a choice you can make. And finally, if you're dealing with particularly highly software-centric projects, you can dispose of the physical architecture altogether and just work in the logical architecture, because why have two layers when you only need one? Physical architecture. So the physical architecture, the idea here is to define precisely how something is built and how the various subsystems are deployed to the different locations that you might have. So the physical architecture should form the basis for your design synthesis, your most detailed overall technical solution documentation. Okay, for me, the physical architecture aligns really well with technologies and domains that are already very well understood, like transport and infrastructure. It helps us separate out the concepts of logical and physical architectures with the way that we arrange physical links and component and functional exchanges, which again, with respect to the interface documentation that I've seen, again, very useful in that it's aligned with the way that the tool works. We can show the deployment relationships where we take a thing and say, well, you deployed over here, and you deployed over there, and you deployed somewhere else, and we can see it easily and graphically using some of the architecture blank diagrams. And something that I'll come back to a couple of times is the functional chains are incredibly important, because when we take the high level requirements, they translate, in particular the functional ones, they translate quite well into a functional thread at a more detailed level. So we can see how a particular requirement would map to a high level requirement, a system level requirement would map to a functional chain, and then we can see how all the various components work together to achieve that high level requirement. So it's a manner of tying together low level functions, which should equate to lower level requirements, back up to a high level requirement. So just a quick note, it's also worth remembering that Arcadia is recursive. So we can take a small component, we can focus on that component, and from a high level system, and we can turn it into the system of interest rather than a component at the next layer of recursion rather, and then we can do that again, and we can keep doing that until we have a tree of different models that all work together and are all kept consistent from the top down. So just focusing again just a little bit on the physical architecture, there are some other things that I think were a couple of other things I think were particularly worth noting. So I talked a little bit about the separation of the structural elements and behavioral elements and being able to deploy one to the other. I think that's very useful in the context of things like building services and structures in architecture. And repetition. Repetition is, for me, one of the key things that separates a transport or infrastructure project from other types of project. When you think about the building of something like a combat system or a satellite or something like that, you focus in on one instance of the platform, and you have very much one instance of each of the different subsystems normally. But when we look at transport and infrastructure, what we see is repetition everywhere. We see multiple different stations. We see multiple different sections of track. We see multiple different floors in a building. We see multiple different air conditioning runs, multiple different distribution boards. So there's a lot of repetition. So the REC and RPL paradigm, the reporting and replicating paradigm, is something I want to spend a bit of time on. So, and not only that, but Capella has, once we consider all this, Capella also has quite a strong document generation capability as well, which can help keep massive amounts of documentation, particularly repetitive documentation, up to date for us. All right, so just take a quick step back and have a look at the layers again one last time before we focus in on a physical architecture example to demonstrate a couple of these concepts and how I would normally wish to use them on a transport project. Operational analysis, great if it's a greenfields project, very conceptual if it isn't, to be used sparingly. System analysis, very useful in terms of defining scope, in particular on a brownfields project, so you know what's in and what's out. Logical, it depends. There are many different versions of logical architecture, and you may consider not even using them at all. Physical is where I think most of the work should be in a transport and infrastructure project, because the solution is well understood. Most of the projects are brownfields, and there's a lot of technical detail that we need to capture along the way for construction and to flow down to design. So I say this, but I need to put a caveat on it. General advice only. Please consider the needs of your project, and getting the balance between these layers right will give you the best bang for your buck, will give you the best return on investment. You don't want to do too much modeling, it gets very expensive very quickly. But you also want to avoid rework as well. Okay, so let's have a quick look at a simple example that I've prepared, a relevant transport/infrastructure subsystem. I have selected a passenger information system, but equally I could have picked an electrical distribution subsystem, an HVAC system, fire protection, any one of a number of different subsystems, because there is a pattern, and I've noticed this pattern after modeling many of the same things several times over. So let's have a quick look at what that pattern looks like. So here we have and please don't shoot me over the very simplified example that I have here. I don't know exactly how much I've got wrong, but I'm sure I've got stuff wrong. So here is my passenger information system. What I have at the heart is the passenger information server. So some sort of control system that may or may not be co-located with the rest of the subsystem. We then have some form of localized deployed equipment that then distributes the service, in this case passenger information, but could equally be electrical or cool air or fire water or any one of a number of different things. And then we have a series of endpoints that may in fact be designed differently. We have different air terminals for HVAC systems and passenger information systems. We've got large wall displays. We've all seen those. The smaller ones as you walk down a platform, and we also hear announcements over a speaker. And we also have something further upstream that is providing information that the subsystem needs. Right. So hopefully you can all see that this is a feasible passenger information system, and B, I could have easily have used any one of a number of different examples. This could be a distribution board or an air handling unit. It could be a local fire panel with these as detectors. It doesn't really matter. All right. So on top of this, we can now overlay our functions, and this is a powerful view. In my view, I've always liked the architecture diagrams in Capella. It's one of the main reasons why I've stuck with Capella as a tool for so many years. This allows us in one view to see how the functionality is allocated to the different components. We can see the conceptual interfaces between each of the components, and we can see using the functional chains the high-level things that the system needs to achieve that would map to the requirements for the subsystem. So update real-time locations, provide visual train info, and provide audio train info. And by looking at the path of the functional chains, we can see which components are playing a role and what their role is in achieving that high-level objective. Again, very powerful. But they're boxes and arrows, and it's a very functional view of the world. From a non-functional view or performance point of view, or indeed any other viewpoint, we may wish to capture additional information. So fortunately, Capella allows us to define a whole or any number of additional structures of information that we can then attach to any of these objects. So here I've attached some simple non-functional style requirements. We've got a weight requirement there, perhaps a restriction on the model, and a performance requirement there in terms of bandwidth. So we can attach that as information. So that's really great. But this is all still fairly basic. The next thing we've got to do is actually deploy the subsystem to something real, something that we actually want to build, because that's what transport and infrastructure is all about. Okay, so let's start with a simple case. So here what we've got is we've now got these behavioral elements, right, in the blue, and we've got the structural elements in the yellow, and now we can see the mapping. We can see where we have deployed this the subsystem, and we're not reduced here to a text representation. We can actually see this graphically, and again, a lot of other tools reduce this particular style of information, this deployed to information down to text. I find it much easier to work with visually. So we can see that here with the passenger information server that's been put in the control facility. We've got a comms room within the station building, and then we've got some endpoints deployed to the concourse and to the shelter on the platform. And we've got the train location service coming from the track and surrounds and pumping that into the passenger information service. So that's great. Now we can see where we have deployed our conceptual architecture onto our actual physically deployed architecture. That's great, but that's not a complete picture yet. What we need to do now is we now need to add in the actual physical connections. So now that we've taken our more conceptual style architecture view and we've deployed that onto the here are the actual structures and locations view, now we can actually define the actual physical links. So we can see that we're going to need some network cabling going from the control facility through this abstracted away trunk comms facility. I apologise to any comms people who are on the line, but I'll get back to you towards the back end of this presentation. And we can see that we're going to need cable runs from the comms room to the shelter to handle all of this, and we're going to need and the track and surrounds is going to need to connect to the trunk comms to supply this information. So we're now taking conceptual, mapping it to physical, and again we've got these two sorts of logical conceptual view and then the physical view on the one diagram, which is useful. And then we can fill that out. We can fill that out with the functions, so we can see where the functions are actually deployed now, and we can see the functional chains, which again are traced to top-level requirements, which we can actually see here. I've got a couple of top-level requirements here, which I've traced through to the functional chains, and they so we can see that each of these functional chains represents, again, that top-level requirement, and then we've got some low-level requirements here. I'll focus mostly around on some interfaces between these two parts here for the sake of this presentation. We can see how because we've captured a complete model now with functional interfacing, conceptual interfacing, and physical interfacing, as well as the functions at either end, we can capture a whole range of requirements and really make sure that we haven't missed anything. Who would have thought we could end up with 1, 2, 3, was it 4, 8, 9 requirements to describe the interaction between these two simple things, but you can, and we make sure we don't miss anything because we've got this view. Okay, so it's great, but it's still very simple. All right, we've got a very simple example of some sort of building service deployed to some form of structure. But again, that's not how real systems are built. The way real systems are built, again, is with repetition. And what we're going to see are multiple stations, which are going to have many instances of the building service deployed to it. And we're going to have multiple endpoints as well. And again, that is the equivalent problem as what we would see in any other building service style behavioral system. It's going to be deployed to a bunch of different locations. HVAC will have a bunch of different air supply duct runs to a bunch of different locations. There'll be a number of distribution boards throughout the building. So how do we deal with this? Well, we deal with this through the Rec and RPL feature, recording and replicating. I've got a little video here, which hopefully if I find the play button, there we go. What I've done is I've taken a recording of the station structure, and I want to show you what I did so I can have a quick look. So I've captured a bunch of elements in the model. You can do that just by grouping them on the diagram, and then you can instantiate. So in this case, I'm creating another station structure called next, so next station, station next. And what we can see now is that I've now got another station because I've used the record and replicate functionality, and it's got all the same elements as the original station. So now I want to bring that into the diagram because for whatever reason I wanted 2 stations on this diagram. So I can pull across all of the elements from the next station, and okay, we get a little bit of a mess, but that's okay because again, one of the features here which helps with repetition is we can copy and paste the format and the layout. So here I'll just paste the layout, and voila. I've now built on the single example that I've done, and I have very quickly created a whole new station, or at least the structure for a whole new station. All right, so that's given me the structure, but now I need to deploy the building services element. So now I've got the station passenger information service, and I'm going to create this, and I'm going to call it also underscore next. So passenger information service next. Okay. And what we should then be able to see is the station passenger information system _next. So we can now just grab all of those elements, not the top level abstract one, but we'll grab everything else, pull those across into the diagram, and just roughly speaking, move those around until we get them in more or less the right place. Okay, and then once again, we can just paste the layout. So let's do that, and there we go. Again, repetition. We can make use of the tool features to allow us to do things more easily, and we can then finish the picture by showing that we've got all of these requirements. Now, one of the things that perhaps is not so easy to see on the screen is that when I took this recording, I also recorded the requirements that were relevant and pasted the requirements. So now what we see, if you look just over here, is that we've got multiples of requirements. Some are recs, some are RPLs, and what that means is that I can use the features of the tool not only to make sure that I've modeled something properly, not only to make sure that I've accounted for all the requirements, but then I can use the tool to do the repetition necessary for the scope of the project, and make sure I still create all the right requirements. So again, another feature of Capella that just helps us through the process of doing the systems architecture for a transport or infrastructure project. All right, now, in the interest of time, I'm not going through another video. What you can also do is you can take recs of recs. So what I actually did in this model was I took the passenger information system speakers and created a secondary rec off the next station, and did another RPL for the end of platform speakers. So this then allows me to take the basic deployed building service sort of system, deploy it to a location, and then I can take each of the different conceptual elements. So again, this could be CCTV and different types of cameras or whatever else it is that's important to you, and you can now replicate that for however many of these that you actually need. And again, you don't need to model absolutely every single camera or absolutely every single set of speakers if you don't want to. Indeed, I think there's some value to having assets underneath a sub-assembly, but whatever replication you need, we can use this methodology. Next, so that's all fine and well, but what happens if the design changes? Okay, so and again, this is very important because so often on transport and infrastructure projects, we do this sort of general design. And we say, right, we're going to have a network that looks a bit like this, or we're going to have a passenger information system that looks a bit like this, or a CCTV system that's going to fit these specs. And somebody will do that, and then somebody else will then go and do the design for the specific locations, picking up the bits and pieces of the original design that somebody authoritative, some sort of subject matter expert has provided. But what if they change their mind? What if they make a change? Well, fortunately, what we can do is we can update our RPLs from our recs. So in this case, I'm making a small change. I'm going from passenger information system to PIS. It could be a much broader change, adding things, removing things, and so on. But in this case, I've simply made a small change. So now what we can do is we've made an update, so we can update the rec. We click on the thing, we trust the tool, away we go, apply. So now we've updated the rec. So now that we've done that, now we should be able to update the any of the RPLs. So we'll do that. Trust the tool. And now we can see that the next station now has PIS speakers next. And then we can complete the process by going to all of the other deployed instances by then updating the rec and the RPL for the additional sets of deployed speakers at this location. So we might just hurry that along a little bit. Trust the tool, do the thing, and we should see this updated very shortly as soon as we update the RPL from the rec. And there we go. So you can make fundamental changes that then flow through to the rest of the design across however many stations, however many floors, however many rooms, all require the same design change. You'll have about as many button clicks as what we've just seen for a simple example. Because you're simply updating the recs and the RPLs, you're not having to go through and add things and change things constantly. Okay, so back to interfaces, because I did want to talk a little bit about interfaces. Interfaces are one of the key things that we need to make sure we've got well documented, because we've got different suppliers, potentially different constructors, different work packages. It seems to be one of those key things that you not only end up having to manage design, but you also have to manage contracts and organizations. So it's good to get it right. So I'll focus here on an interface here between a control facility and a deployed station. So we've only got one of these, and perhaps we've got different contractors for each of the different stations. So we've got to try and make sure that we've got all of this right. So what we can see here, again, we emphasize that we've got the physical interface there going through the abstracted trunk comms system. We've got the conceptual interface there with the component exchanges, and we've got the functional interfaces, and we can check and make sure that we've got everything covered off. So that's fantastic. Quite often, unfortunately, as systems engineers, we actually have to talk not just to systems engineers, but also to humans. So we need to be able to take this information out of a model that a systems engineer would be happy working with and put it into a document that a human would be happy working with. So what I have here is just a very, very short example that I pulled together. A couple of paragraphs worth of code to build a document generation template. And I've been able to produce a comms document that has included the diagram, specifically the one I was after, and then listed out all of the requirements associated with this interface. I could equally have pulled out all of the physical links, all of the conceptual interfaces. I could have associated with them, could have done a whole number of different things. But for the sake of a simple example, I just wanted to show you that couple of paragraphs worth of code into a document template, and you're away, because now I can reuse this again and again and again and again and again for all the repetition, for all the interfaces that I might come up against. So that abstracted away trunk comms subsystem. It's great to have a low level of detail here so that we're not diving into things that don't really matter in terms of the functionality between the deployed elements of the passenger information system and the control facility. But for the poor comms guys, that's not really good enough. We're going to need to dive into a lot more detail here. So Capella allows us to have things abstracted away at the top level, and then we can focus in on a subsystem, let's say trunk comms here, by doing a system to subsystem transition. And that allows us to take an element of the model, and it allows us to then treat all of the interfacing elements of the model as the actors. And now we've got a system and the system analysis layer, and now we can dive into that and create a far more detailed model, a far more adequate, perhaps, ICD for the trunk comms system and design and so on, all while keeping it consistent, because having done the transition, it's now joined, and we can continue to flow information from the top level model down. Ad hoc reports, data. Fortunately, Capella has got a handy little Python interface, Python, the #1 programming language in the world these days. And it comes with a set of sample scripts that you can hack, like me, to produce whatever report in a CSV file that you might be interested in. So you can produce a report that shows the number of widgets, and specifically what the widgets are that are connected to something else, or that have requirements, or are missing requirements, or requirements that are missing traces, anything you can think of. So final thought, having been through all of that. So I've shown you, I think, how I have modeled transport and infrastructure projects in Capella. The key thing for me is the repetition, the ability to interface with using things like Python for Capella has been fantastic in terms of integrating with other tools, things like doors and so on, being able to produce reports that are human readable and so on, having those different levels, focusing in on the physical architecture for a transport and infrastructure project. And remember, at all times, all models are wrong. Never try and make something perfect. You will be there for literally forever. You need to understand what the problem is that you're trying to solve. You need to understand exactly how it is the model should and shouldn't contribute to that answer, and therefore you should know when to stop. So, thank you all for listening to me. Romain, I don't know if there are any questions, but I guess I'm happy to sit here and answer them.
Yes, so thank you very much. First of all, Tim, that was great. So now, it's time for some questions. Yeah, so what would you say would be the challenges in adopting Capella and, of course, the associated Arcadia approach if organizations have been using or exploring other MBSE tools?
Yeah, okay. So I think if people have been exploring other MBSE tools, then at the very least, they will have a good understanding of what constitutes model-based systems engineering. Where I have seen some interesting challenges is other MBSE tools have their own methodologies, and that then shapes the way that the people who are trained in those tools think. To some extent, you have to unwind that thinking and wind people back up again in terms of how Arcadia does things and presents things. And that's about the differences between the way the tool sort of pushes you. So, for example, an activity diagram in SysML isn't quite the same thing as a functional chain description diagram in Arcadia. In Arcadia, that's what we have is a dependency graph. So we're looking at the different functions and what those functions are dependent on, as opposed to the activity diagram, which says this function is executed and then this function is executed. So it's showing execution order, not dependencies. All right, so there's a certain change in the way people need to think. In terms of the benefits, the ease of repetition is a big one for me. There are some other tools out there that struggle, I think, a little bit in terms of being able to do the same sort of Rec and RPL style package that you can get with Arcadia. In particular, the ability to package up at the same time things like requirements, functions, deployment relationships, all of that into the one package, and then click the magic button and boom, you create a new one. Other tools have less of a militant approach to enforcing semantic rules. So I see some of the benefits there in a large-scale project with rules being enforced and the generation of documentation. You get a much more consistent set of documentation, which is important if you want things to be built properly in the same way each time. The other big advantage that I've really enjoyed, and I guess I didn't talk about it too much because it's more of a general tool advantage rather than a specific transport and infrastructure viewpoint, is the Python for Capella interface, right? The ability to jump in and code something and produce 100 copies of something very quickly, because you needed 100 copies of something very quickly, to be able to pull that information out, make mass changes, do linkages, mass deployments. It's massive in terms of a time saver, and it's also very important in terms of integration with other tools, right? Because you want to be able to produce something out of Capella to suck into some other tool, and you want to be able to take something in XML or CSV format or something that's readable, and then run a script over it to then suck that information into Capella. Hopefully that answers your question.
Okay, that's great. So here another question. So do you also focus on life cycle analysis of the components for e-waste, for example, when to integrate COTS components? So I can give some elements here. So there is a project called Eco Design for Capella, which is an open source project that is pretty useful to connect your Capella model to your lifecycle analysis tool, and to compute the ecological impact of your system, to compute carbon emission, and basically to integrate Capella with the lifecycle analysis tool. So if you want to learn further about that, you can explore the Eco Design for Capella add-on online.
Yeah.
I don't know if you have something to add, Tim, on top of that, or we have a last question.
I would say if you're not going to go the whole hog with an add-on, property values, the PVMT add-on, it would be a good first step to try and capture information that you need to. I can see that Kitaki's question has been updated. Did you want to have a quick look at that one?
Yes, sorry, I didn't get the end of your question, Tim.
I think Kitaki's question has been updated. Are you able to bring that one up on screen?
Yes.
I think it's important to answer that one.
Yes, so why not scenarios considered, and how do you represent interfaces in your diagram? Normally, it should be at logical architecture or physical architecture.
So I could have equally showed interfaces in scenario diagrams. I didn't show everything because I could easily have rattled on for at least half a day if I were to show everything. I think scenario diagrams, no, I'll take that back a step. Quite often, functional chains are very close to good enough in terms of being able to show a scenario, at the very least a sunny day scenario, because you can see the dependencies. And in simple cases, you can add a scenario and just show a single thread flowing through each of the different lifelines, and then you get to the end of that and you think, well, great, what did I really add by doing that? Where I think scenario diagrams add value is where you have some sort of temporal complexity, where you have loops, where you have certain dependencies needing to be fired off 5 or 6 different times before the subsequent depending function is able to be executed. So, or if there's states and modes involved, scenario diagrams are absolute gold. So I certainly wouldn't exclude them, and I certainly do use them, but I use them where they are going to add value in describing the temporal complexity, and then teasing out some of those additional requirements that you need to cover off. Now, in terms of LA or PA, I think if you're going to show interfaces in the logical architecture, then that's very much dependent on what the goals are for your logical architecture. The logical architecture is a bit of a fuzzy layer. It means different things to different people. System analysis layer is pretty clear. You draw a box around your system. What's in scope is inside the box. What's out of scope is outside the box. Physical architecture, again, very clear. Show me the boxes that you actually need to buy and build and deploy. Logical architecture sits somewhere in the middle. So you have to be very clear on what it is that you're going to achieve out of the logical architecture. One very strong possibility is if you're taking a scope breakdown view of the logical architecture, you can say work package A is one logical component, work package B is another logical component, and then the interface between them defines how those work packages have to work together. So that would be a way of using interfaces at the logical architecture layer. From a technical standpoint, I think you're going to have more luck in the physical architecture, particularly because it's going to be better aligned with what needs to be done for a transport or infrastructure project.
How would you go about encouraging the Arcadia approach in Capella for mechanical and structural engineering fields that would rely on more traditional forms of documentation? So,
yeah, that's a really good question. I would first of all point out that Capella and Arcadia are systems engineering tools rather than structural engineering tools. So we need to understand what the role is of mechanical/structural engineering within the context of the system to understand how much modeling we actually need to do in Capella. So mechanical, there's obviously the HVAC side there, and that would be fairly consistent with the example that I demonstrated today. From a structural point of view, we have to remember that the purpose of the node components is to show the parts of the system that are not behavioral, but provide the necessary resources for a component to exist, like the structure. So I think the interface for structural engineering would be in identifying clearly how the different parts of superstructure, substructure interface with other things such as the rooms that an architect might define, and understanding if there are any specific interfaces that you actually need to manage between, let's say, the substructure, the slab, and hydraulics. Where are you going to need to account for penetrations, and how you're going to model that? Do you model that? Can you add property values to the node components to handle the non-functional aspects of what you need to capture? So I think it's a many-part answer. Hopefully it's covered off a number. All of the possible ways I could read the question, but structural components are more likely to be node components, I think, and therefore the interesting things are what gets deployed, what does that deployed interface mean, and what are the non-functional what's the non-functional metadata you're going to capture as property values or something similar.
During your presentation on your passenger information system, at the physical architecture level, there were some tick boxes representing requirements. Are requirements only elicited in this view, or can we also elicit requirements at OA,
No,
SA, and logical?
They can be elicited in any view, in any layer. So if you want to work in OA, SA, LA, that's perfectly fine. So hopefully that answers your question. And you can even show traceability between levels of requirements in Arcadia if you really wanted to do that outside of doors.
Could one potentially use LA and PA to describe generic and specific application in accordance with CENELEC standards? So are you aware of this standard?
There are a lot of CENELEC standards. I'm wondering what Donovan has in mind. reusable framework designed for a class or type of application, sharing common functions. A specific application is more focused version of a generic application where a generic framework has been customized with a set of parameters for use in a particular singular installation system. It sounds like what you're describing is a relationship between a logical architecture and a physical architecture, in that if you take a generalized architecture view for logical architecture and a technology specific view for the physical architecture, that's one possibility. If you don't have a great deal of variability between your customized solutions, and it's more about multiplicity of different aspects within that solution, then Rex and RPLs might be useful. And Python for Capella is always very useful for if you don't want to do things manually, as long as your programming skills are up to it. I hope I've answered your question, Donovan. If not, just give me a buzz later.
Thank you very much for joining this webinar. Particularly, thank you very much, team, for this presentation. That was great. Also, thank you everyone for all of your questions, and team for your answers. So thank you very much all. Thank you all. Bye.